Hey guys, welcome to Learn True Tech. In this video, we'll be understanding one of the fundamental algorithm in machine learning, linear regression. This is the first video in the basics of machine learning series. Before understanding the fundamentals of linear regression, let's try and solve a problem. Given the area of a house, you got to tell me what's its price. So the first step in attempting to solve this problem is to find a data set. Basically go around your locality, knock doors, and ask them the area and the price they're willing to sell and tabulate them. We have done the hard work for you and created a synthetic data set of area and the prices. So from the data set, the aim is to learn and understand the relationship between area and the prices and use that relationship in order to answer new queries regarding this problem. So this is the plot of the data set, and we have 9 samples in total. So now that we have all the samples, the next step is to find a function that maps the area to the prices. Basically, we have to find a function f of x, which when given area as input, gives out the price. But what's the function? How do we find it? So one simplifying assumption is, we can assume the function to be a linear function. So what is a linear function? A linear function is a function whose graph is a straight line as shown in the video, and a linear function generally has a form y equal to wx plus c, where x is the independent variable and y is a dependent variable which depends on x through this relationship wx plus c, where w and c are constants. So why do we particularly choose a function like this? There are several reasons. One way is this function is very easy to implement. That is very simple logic, so super easy to implement, and it's quite easy to debug if any problem arises. Interpretation is very simple. If you have multiple features, it will be easy to find which feature actually drives up your model output. And since it's very simple, it also is computationally lightweight and runs quite fast. Now that we have decided that it is a line, there are so many lines in the 2D plane. So how do you decide upon the best line which represents the data? So let's take 3 examples. So we have shown 3 lines that presumably fit the data. Like, try and answer which line actually is the best in representing the data. It's quite simple, right? So the plot which is highlighted here actually best represents the data, but why? Intuitively we know like this is near all the data points, but let's define it a bit more strictly. In this plot, for example, a house of 2,100 square feet is about $12,000 in price, but our model has estimated it to be $14,000 and we are off by $2,000. So basically we can take the difference between the real value and the estimated value and sum them up and use that as a metric to find the goodness of the fit. But there's one catch out there. The fact is, there are some regions where our model overestimates the price and there are some regions where our model underestimates the price. Therefore, the deviation can be positive and negative. So summing them up can give a wrong picture. So we can square them up and make them positive and then sum all the square deviations, and the line with minimum sum of squares actually can be considered to be a line which better represents the data. So under that method, we see clearly this is out of the picture because deviation is very large, and out of these two it's quite clear that this has minimum deviation. So now that we have the intuition clear, let's go ahead and be a bit more rigorous. What we discuss now is what we call as mean square error. The mean square error is defined as follows, where xi is your input. In our case, this is the area. So f is our model. So f of xi is a prediction. So basically f of xi minus yi is the deviation that we saw in the previous slide. So f of xi minus yi squared is the square deviation, and basically we are taking the average of all the square deviations, and that is what we call as mean square error. Basically, the line with the smallest mean square error is said to be the line which best fits the data. So mean square error is just one such metric of a huge array of metrics which are available to describe the goodness of fit, but this by far is the most widely used metric out there. There are so many reasons as to why this is so widely preferred. One such reason is continuous and differentiable and all those nice properties. And in this specific case of linear regression, this gives us a closed form solution and it's very easy to implement. One of the cons of this loss function is very sensitive to outliers. So outliers are actually data points which are very far away from the majority of other data points. In other words, they are unusual values in our data set, and therefore sometimes the deviation tends to be quite large, and as we are squaring the deviation, those numbers can become ridiculously high and sometimes can cause problems in optimization and final fit. There are several ways to circumnavigate that problem, which we will see in the future videos. Now that we have the concepts clear, we can go ahead and implement it in Python. Alright, let's get started coding. So first, let us import all the necessary libraries. We'll be importing NumPy and matplotlib for plotting purposes, and SKlearn to use its linear regression module. Import NumPy. And also importing SKlearn. Import linear regression. So now that we imported the models, let's create a data set. Create a sample data set. So first we can create 9 samples. And area is basically we are taking uniformly spaced points from 800 square feet to 2500 square feet, and those are the area. And the price is, we are assuming it to be 5 times area plus 700. Well, this is the true function which is not known to us in real life, right? So what we'll do is we'll create price to be equal to price plus np.random.randint, right, from -1000 to 1000 now. So basically what we are doing is we are creating a noise vector of random integers from -1000 to 1000 and adding it to the price and corrupting the price, and this is the price which will be revealed to us. So basically our data set is area comma price, and now using that data set we got to actually perform our linear regression. So what is our aim? So basically we are saying price to be equal to some constant times area plus another constant c, and we have to estimate w comma c, for which we'll be using linear regression technique. Alright, let's go ahead and reshape area to be area dot reshape of -1 comma 1. So basically we are reshaping it so that it comes of the form n samples comma n features. We have one feature which is the area, and we have 9 samples which is equal to n samples. SKlearn has the standard of accepting a data set of this shape. And once the reshaping is done, now we are getting into the real stuff. We have to initialize SKlearn's linear regression module. So reg is super easy to initialize. It's just linear regression. That's it. You have created an object, and now we have to fit, right? So in order to fit the line is reg dot fit. We have to give the area x and the price, which is the label y, and this is for fitting the data. And once the data is fit, we can run this out. It's over. So we have fit the line, and the line coefficients and everything is considered in this. The line coefficients are actually present in this object. Now we got to predict the data, and we have to plot our estimated line and the data set. So basically, let me create a new variable. Est price is actually reg.predict area. So basically we are giving area as input, and we are calling the predict function attribute function in reg, and basically that will give us the estimated price. And now we have the estimated price, we have the true price, we have the area. We can plot them and see how fit looks. So first let's plot area price, that is as a scatter dotted plots. I'm having label to be, this is the data that we have, and let's plot our estimated price, and this label is our estimated line. Then let's have some X label. In X-axis we have area, in Y-axis we have the price. Just give a title, you can give it as price versus area, and let's have legend in the plot. Oh, there's a small error, it should be lock. Okay, yeah, there you go. So basically this is the data point that we have, and this is the line which minimizes the mean square error, and you can see it pretty much passes through and represents the data quite well. So now that this fit is done, and now this linear regression is over, so let's say some house comes as a query with 1487 square feet as its area, and the task is to estimate like what would be the price. So how would you use this model to estimate? So basically what we will do is 1487, where it is will be on this point, this area, so 1487. So the function value is somewhere around 7500, 7000 to 8000. So basically that's how we will do it. So in coding we will do it like this: predict test area, and you see it's around 8100. So basically what we are trying to say is a house with sample area. So we are trying to say, using a model, that house with area of 1487 square feet will be costing around $8,100 according to this model. So this is how we have to code, and it's very simple. Thank you for watching. If you have any doubts, any suggestions, any improvements, please comment down below and subscribe, and see you next time.